Okay, so let's get started. So tonight we're talking about supercontinents. Have you heard of such a thing, a supercontinent? You've maybe heard of Pangea. Is that a name that rings a bell? Yeah. We'll talk about Pangea, but it's not the main focus tonight. We're going to go way back into history. We're going to go back hundreds and hundreds of millions of years before Pangea to earlier supercontinents. Oh, the room got quiet suddenly. Like, what? Really? Yes, there's even names for these earlier supercontinents than Pangea. And then before our mind is just going to blow up and just burn and smoke and everything, and we can't handle all of that, we'll take a break and we'll go to the Pacific Northwest, because this is a geology lecture that focuses on rocks of the Pacific Northwest. And we're going to look for some rocks that can tell us something about that cycle of supercontinents. We've got to find some really old rocks to do that, but we can find them, and we'll feature the Belt series tonight for those that know geology very well. That's our game plan. 30 minutes of chalkboard, 30 minutes of visuals, and hopefully we're feeling a sense of accomplishment by the time we're done with this thing. Are you ready to go? Okay, let's do it. Wonderful. So this is a black chalkboard. Let's pretend that it's a world map. A world map from your youth in front of your grade school classroom. Can you picture a world map in your mind? How many continents are on that world map? 7 continents, that's right. And there's a handful of oceans between North America and Africa, the Atlantic Ocean, the Pacific Ocean. Okay, fine, good. Are you aware that if we pull down a different world map for 200 million years ago, it will look very different? In fact, there'll be one continent on that world map for 200 million years ago and one ocean. And that one continent was a big, big continent. In fact, it was a supercontinent called Pangea. Let's write it out. Pangea. P-A-N-G-E-A. That's one way to spell it, and that's how we're going to spell it tonight. 200 million years. Again, we're going to be working in hundreds of millions of years, even thousands of millions of years tonight. More than 1 billion years. So one way to view Pangea is, okay, it was a supercontinent, and in the last 200 million years, Pangea has been breaking up. It broke into 7 pieces, our 7 continents, and those continents continue to drift away from each other. There was no Atlantic Ocean during Pangea. You could have walked directly from New York to Morocco in Africa. And in the last 200 million years, the Atlantic Ocean has continued to grow in width, and the Pacific Ocean has been shrinking in width. 4 inches a year. The Atlantic Ocean grows 4 inches wider every year. That's pretty fast. We have GPS measurements to document that. Christopher Columbus did not have as far to travel as we do now. Insert laugh track. Okay, great. So if we open Pangea, if we open the Atlantic Ocean as we break up Pangea, we're actually closing the Pacific. And so one way to view Pangea breaking up is we're heading for the next supercontinent. We're closing the Pacific and opening the Atlantic. Now, if you're aware of Pangea, and I think most of you are, maybe you assume that Pangea was the way Earth was given to us. Like Pangea was the original configuration, and there's just simply been this breakup. I think a lot of people think that, without thinking about it a whole lot. But how old is the Earth? This is a science lecture, right? How old is the Earth? It's 4,600 million years old. The Earth is 4.6 billion. And I want to stay in millions tonight. I don't want to go back and forth between millions and billions, okay? So 4,600 million. So there's a lot of time before Pangea. That's the next concept. There was a completely different global geography that's almost unrecognizable to us before Pangea. Therefore, there was a time that we assembled Pangea. Yes, like a jigsaw puzzle. That's the common analogy. Put the pieces of the puzzle together. So Pangea, supercontinent, was together for 100 million years. That's worth thinking about for a second. That's a long time. Dinosaurs were alive during when Pangea was together, and dinosaurs were alive when Pangea started to break apart. 100 million years for one continent and one ocean on planet Earth. But I got room, and I got a piece of chalk, and I'm going to write down 2 other names of 2 other supercontinents that we now know about that predate Pangea. Let's get to it. Rodinia, Columbia. And you're like, wait a minute, I like geology. I read about geology all the time. I've never heard about either of those. Well, they're pretty new. The proposal for the supercontinent Rodinia got into scientific papers in the early 1990s. That's not that long ago. Pangea was proposed by Alfred Wegener more than 100 years ago. And the supercontinent of Columbia, sometimes called Nunya, came out in the last 15 years. So this is pretty new information. So don't feel too bad if you haven't heard about it. I knew very little about these 2 supercontinents about a week ago. I've been cramming. Woo! All right? I got a laptop, I got the internet, I can find these scientific papers. I got back from spring break, I'm like, oh my God, I got a lot of work to do on this lecture. And I started emailing these authors, these researchers, in addition to reading their papers. And I've got some good stuff for you. I've got some good stuff for you about Rodinia and Columbia. I can't hold it. I got to say the first major message. The Pacific Northwest have rocks that are all about these 2 supercontinents and not Pangea. Pangea is too new for us, too young for us. So Rodinia was assembled more than 1 billion years ago. 1,100 million years ago is more than 1 billion, right? And 750 million years ago is when Rodinia started to break apart. Let me finish the blackboard here. Columbia, 1800 to 1400. There's a supercontinent cycle. Assemble, keep together for hundreds of millions of years, break apart. We live in a ball. If we break apart a supercontinent, they're going to get together somewhere at some time. Next supercontinent, break that apart. Next supercontinent, you get it. And just like all kinds of history, the further back in time we go, the less we know. We know by far the most about Pangea and very little about Columbia, but enough to include it in this lecture. And I do feel, for the sense of completeness, that there are earlier than this supercontinent ideas, but those are really scraps. It's not worth it, in my opinion. Comfortable? Head spinning? Too much time? Can't handle it? Looking for the nearest exit? All right. Maybe I figured that was the case. So I'm going to keep this on the stage up here as a reminder. It's not going to change the rest of tonight. And now I'm going to work with these 2 guys for the next 20 minutes or so and try to use Northwest geology to somehow eventually plug back in. Okay, so let's switch things up. I think we need a break from this. Let me tell you a story. And the story takes place in a national park that's right there, Glacier National Park. So the story involves my favorite subject, me. It was the summer of 1983. It was the summer that I was turning 21 years old. I was going to school in Wisconsin. That's where I'm from, Madison. 3 years in college, no direction, no major, couldn't find anything that interested me. Ran out of money, basically. Took a train from Madison, Wisconsin to Glacier National Park in June of 1983. I mean, how old am I? I'm taking the train, for goodness sake. It's not that far. I didn't have a car at the time. Great. My summer job, was to work at Lake McDonald Lodge on the west side of Glacier Park. Many of you have been there. There's the lodge, there's the general store. There used to be a little gas station, and my job was to pump gas and to sell souvenirs at the general store with a bunch of other college kids who were there for the summer from all across the country. I'm telling you this story because it was my first time living in the West. It was my first time hiking in the mountains. And it's the summer that I discovered geology. I had no interest in geology before that summer. But I did these day hikes. I did these visits to these places that really surprised me. First of all, the scenery was beautiful. We all have that experience. But there was one particular day hike I want to tell you about as quickly as I can. I've got photos I'll show you from that actual hike in 1983. We're going into the archives tonight. So Craig and Webb and Bruce and I jumped in Craig's car. We drove from Lake McDonald up the Going to the Sun Highway to Logan's Pass. Many of you have been there. We parked right at that big parking lot early in the morning. We hiked north on the Highline Trail. Pretty easy walking. And then at some point, Craig said, "We're going to the top of Mount Gould. Are you ready?" Mount Gould is the very top of the Continental Divide in Glacier Park. It's the top of the Garden Wall. And we're all in our early 20s. Do you remember the days where you could just walk up a mountain with your hands in your pockets, essentially? I miss those days. So it was 2 o'clock in the afternoon. We're on top of Mount Gould. We're up high enough that it's a bluebird day and we can see out to the plains of Montana. Some of you have experienced that. You're up that high. You can look down on Grinnell Glacier, down on Many Glacier Hotel. And I was a greenhorn. I was literally wearing my farm boots, from Wisconsin. All these other guys had all the hiking gear, but I was new to the whole scene. And we had lunch. I had my little PB&J and a little packet of Skittles, I remember, and I was sitting on this maroon rock up there in the top of Mount Gould. And the other 3 guys were about 15 yards away from me, sitting on a different rock. And at some point, Craig broke the silence and said, "Hey, you are so out of it. Why did you pick that rock to sit on? Isn't it uncomfortable?" And I'm like, "I don't know." He said, "You're sitting on a bunch of those ripples. Have you noticed? Aren't you uncomfortable?" And it's true. I was sitting on this slab of maroon rock that had these beautiful, symmetrical, petrified ripples on the surface of the rock. And I was like, "Oh, yeah." I had these like red stripes on the back of my bottom and my thighs. And then Craig said, "Do you know how those ripples formed?" In a kind of a show-offy way. And this is 1983. You can't just pull out your phone and like double check what the guy's saying, you know. He was like, "This used to be a beach. I took Geology 101 at Oregon State University and I learned that these ripples formed at the beach." And I'm like, "Yeah, bullshit. That's not good." And he kept talking about this beach thing and the coastline. This was the old coastline. And all the other guys were like nodding their heads. And I'm like, "I don't believe you." Okay, I'll finish the story. Craig was right. Those rocks are Precambrian rocks that clearly formed at the old coastline of North America, here. And those rocks are all through this area. Let me draw a line for you. This is a very clear line on that map of the Pacific Northwest, and that line is the true coast of the Pacific Northwest, or the west coast of North America, for hundreds of millions of years. And Spokane is right here, if you can see that gold dot. So pretty much everything between Spokane and Glacier Park, and those rocks continue to the south down to Vegas and even into Mexico and north up through Canada. These are all beach rocks. These are all rocks that are muds and sands. And they are called, at least in the United States, the Belt Series, or the Belt Supergroup. It's where the Rockies are today, but this predates the Rocky Mountains. That was my confusion, eating my Skittles. I'm like, I don't get it. These are the mountains. What are you talking about the beach for? You can go from a beach scene to a mountain scene if you have enough time. And that's what we're talking about here. Collectively, these layers of rock that were originally sedimentary rock and are now metamorphic rock, the Belt Series, located on that map there, Glacier Park, Spokane, Steptoe Butte, Colville, Chewelah, Medical Lake, Libby, Bonners Ferry, take your pick. All of those plots have belt rocks located there. They're beach rocks. They're Precambrian aged rocks. In total, that cake is 5 miles thick, 25,000 feet worth of sedimentary rock deposited at the coastline of North America. We have dates now. Dates for the belt. 1,500 million to 1,400 million. Seriously old. During that time, we deposited all of those beach rocks. Now, originally, it was sand at the beach and mud at the beach. Those ripples I was sitting on beneath the patch of Skittles was a tidal zone, was a muddy zone. You've been to the beach. The coast of Washington has a lot of mud, right? And you have drying mud that forms cracks. You have the ripples. In certain places off the coast of Australia, you can get stromatolites, these big mounds of blue-green algae, stromatolites that are fossilized in this mud. And sand, we all know sand is at the coastline, at the beach. But originally, the sand got buried into sandstone, and the sandstone got heated up and pressurized to become quartzite. And the mud got buried to become a sedimentary rock called shale, and the shale got buried to become a metamorphic rock called slate, and the slate sometimes turned into argillite. So, what are the belt rocks today? Rocks of this age, representing an old coastline, interbedded layers of quartzites and argillites. Quartzites and argillites. But we don't care that they're metamorphic today. We care that they were originally deposits at the beach. The energy in the room is great. And we're now to the juicy part. We haven't even gotten to the good stuff yet. Now, this is what I've been teaching for a long time. And I would not only draw what I just drew here for you, but then I would say to my students over the last 25 years, where do you think all that sand came from? Well, it's the coast, isn't it? Aren't we going to assume there were rivers draining North America at the time? I hope it's clear to you, Washington doesn't exist yet. Ellensburg doesn't exist yet. Oregon doesn't exist. This is deep ocean. This is open ocean. But we're talking about all this sediment accumulating at that shoreline, the belt, and we're assuming that the rivers are flowing from east to west. And that's true. A lot of the sediment in the belt came from the east, from the interior of old North America, and drained to the coast. You ready? I'm leaving stuff I've taught forever to stuff I've never taught. Stuff that I've learned in the last 10 days. It's good. Here we go. Because remember the gimmick of the lecture, I'm going to somehow say the belt has something to do with this. This is just a coastline, and yet I'm saying there are times when all the continents of the world are hooked together. Some of you are a few steps ahead of me, possibly, especially when I say this. For years, it was clear that when you carefully study the sand in the belt, not all of it came from the east. There were paleocurrent indicators, details written in the quartzites and the sandstones to say a bunch of the sand in this belt came from the west. Now let's pause and think about that for a second. Is that possible? You can't have a river come out of the deep ocean and come onto land and bring sand. There's a lot of sand that look like it came from the west. Next point. There's a new technique we talked about last year and we're talking about again right now. A mineral called zircon. Zircon is a very durable mineral. Many of the sand grains are zircons, and as a geologist now, you can go out and collect sand grains from the belt, analyze the age and the chemistry and the rock type of those sand grains, and find a source, find a place where those zircon grains came from. We couldn't do that before. Are you ready? Both the paleocurrent indicators in a bunch of the belt, especially the lower belt, and the zircon say that a substantial amount of this 5 miles worth of sand is somebody else's sand, is exotic sand, is not sand from North America. There's not a match to interior North America. There's a match where? Somebody else's continent. Now hold on. When we have a supercontinent, we have continents coming together and soldering together for a while before they then decide to split up. Don Winston, who spent most of his career on the belt, he's a geologist in Montana, would have maps and during belt time would say, even in some scientific papers, Don Winston would say, continent X. Continent X. I don't know what continent it was, but it was somebody was here. Somebody was docked right at Spokane and then took off at some point. But the concept is we need continent X because we clearly have a continent with rivers flowing from west to east and depositing the sand into the belt from a different source. Let's pause again, and then we'll reveal continent X. Look at the age of the belt. Does this work age-wise with Pangea? Of course it doesn't. You've already done this. Does it work well with Rodinia? It doesn't work well with Rodinia as well. Look at these dates. 1,500 million to 1,400 million. That's the last 100 million years of supercontinent Columbia, when all the continents of the world were together, when North America was connected to Australia. Continent X was Australia. Now let's draw that and possibly turn your telephones off at the same time. Can we multiply? Can we multitask? These new inventions called cell phones with ringers. All right. Let's do a cross-section of this same thing. Let's put Spokane here. Let's put the belt at the coast of North America. And yes, I revealed it verbally. Let's do it this way. And I have to put an asterisk behind Australia. I'll tell you why in just a second. Australia. You could have walked, if you have relatives in Australia, you could have walked from northern Idaho to Australia. There was no Pacific Ocean at this time. Now, what's the evidence? The evidence is you can study the zircons in the belt and you can find Precambrian rock in the core of Australia that's a match. That's a match age, chemistry, everything else. Same thing here. So on this sketch, I can do this. It even gets better. There are some grains of ours that went the other way. But I have to put an asterisk next to Australia, and here's why. A majority, it's 2019, is it not? There's a majority of geologists in 2019 that say it was definitely Australia. I've written my scientific paper and I've got all this evidence to match the belt of the Pacific Northwest with the belt of Australia. And some old craton on North America and Australia as well. But from this point forward in our little lecture, I'm going to do this every time I say Australia, okay? This means asterisk. Because there are still some holdouts. There are still some geologists who say it was not Australia, it was Siberia. Another group says it was not Australia, it was Antarctica next door, parked at John Stockton's house in Spokane. Even another group saying it was not either of those, it was a piece of South China, Precambrian craton of South China. So there's a chance all four of those are still going to be in the literature for a while. But there's enough people saying Australia, and the visuals I'll have showing these world maps, many of them will have Australia next door during supercontinent Columbia. I don't know how you feel, but that was the big moment tonight. Now I'm telling you how to react. That's cheap. So last time I checked, Australia is not here anymore. It took off at some point. And we have a date for that. For sure, everybody agrees that continent X, most likely Australia, rifted away, began to break away from the Pacific Northwest 750 million years ago. The evidence for that is something called the Windermere Group, and specifically the evidence for that is there are basalts that start showing up. Basalts that have now been metamorphosed into rocks called greenstones, but they were originally basalts. And anytime you have a continent rifting away from another continent, like North America rifting away from Africa during Pangea's breakup, you develop ocean crust in between those rifting continents. You create ocean crust in between these rifting continents. So the basalts, now greenstones of the Windermere Group, is the basalt that formed as Australia rifted away from old North America. Never to come back. Or will it? Will we reconvene and be reunited with Australia at some point in the future, in the next supercontinent to come? The last thing I want to do is very quickly on the chalkboard, and then we will switch to the visuals because I've got lots of good stuff for you there. Australia is gone, but I feel we need to make Washington. If this is a lecture in Ellensburg, Washington, in the Morgan Auditorium, we got to make this state somehow, don't we? We can't just leave deep ocean here. At least I don't think we can. And so if we jump way up here to the breakup of Pangea, and North America is starting to move west as Pangea breaks apart. Let's do that. North America is moving west with the breakup of Pangea. So there goes Africa heading out the other way. And if this is new to you, you'll see some maps. What city is here? Spokane. This line is clearly where Australia rifted away, and that old rift has been there for a long time. It's a very sharp boundary. Geologists call it the strontium 706 line, simply meaning that there's certain chemical signatures in the magmas coming up through this craton material and very different chemistries, strontium differences, with the magmas coming up in this other stuff. So how are we going to build Washington in the last 200 million years? Many of you know this. Last year we did a lecture on exotic terrains, but I want to revisit the main concept, which is we had a huge ocean plate called the Farallon Plate that was coming at us and subducting beneath us. This is ocean now. And we make Washington by receiving gifts from the Farallon Plate. Huge gumdrops, huge exotic terrains of different origins that are riding on this conveyor belt. And as the Farallon Plate continues to come at us, we build Washington piece by piece. And eventually, we build the entire state of Washington. The last terrain to come in made the Olympic Peninsula. And we'll have a couple of visuals. This is a big room now. I can't talk one-on-one with you. Right? So there's a whole scene, there's a whole drama just in the last 200 million years. But this lecture is predating everything we've done in this series. Everything we're talking about here. The Ice Age floods, the flood basalts, the Cascades, the Bridge of the Gods landslide, everything. It's all right up here. This is the first lecture we're brave enough to go this far back in our history. And certainly there will be new data coming about those old supercontinents. This is the moment to say to your neighbor, isn't this interesting? I love this. And while you say that, we're going to get the screen going and the projector. Okay? Give us just a second. Thank you. Okay, the chalkboards do a decent job, but I think we need more. I think we need more professional imagery and some animations and a few other things to make this work. So let's go ahead and take some photos, etc. We've got some really wonderful footage of Glacier National Park. You can see the layering of the bedrock here. That's the belt. These are the beach rocks between 1,500 and 1,400 million years. The glaciers themselves have dug so well recently to reveal all these cliffs. Otherwise, we wouldn't see many of these rock layers. But this is the place that it's quite easy to be introduced to the belt series. They're right there in front of your face. They're on every hike that you do in Glacier National Park. Coastal rocks, and are you looking at this in a different way now? Oh my God, there's grains from Australia in the picture. Now, let's zero in on some of the structures that are in the shales and the sands that are now metamorphic rocks to convince ourselves that this beach story really is true. Look at this. These are mud cracks in a tidal mud flat from more than 1,400 million years ago. Isn't that unbelievable? This is so far back in time, we have no major fossils to bioturbate, to screw up all these very delicate features. So the amount of preservation in these rocks that are more than 1 billion years old is absolutely staggering. These are the stromatolites. We're still in Glacier National Park now. These big mounds of blue-green algae. Think the Great Barrier Reef off the coast of Australia, if you like. Oh, that's ironic. Off the coast of Australia. It's so rare to see fossilized mounds of algae, number one, but to find them in this old setting is truly outstanding. Now, the picture on the right is the best I have for you to show some of these current indicators. Can you see there's kind of some Nike swooshes in some of this stuff? So geologists can study the arrangement of the sand grains and say something about the direction that the river was flowing. And here are the uncomfortable rocks to sit on, the ones that have these symmetrical ripples in the slate that used to be mud. So these maroons and these greens and these purples, if you've been to Glacier Park, you know exactly what I'm talking about. And those are the rocks that we're featuring tonight. From Supercontinent, Colombia. This is a slab that's on display in our geology building here in town. And just running your hands over those ripples is like being at the beach 1,500 million years ago. Now, let's leave the high country where the belt is best exposed, the belt series, and let's go down to Lake McDonald. Lake McDonald, famous for its beautiful, brightly colored rocks in the bottom of the lake. We know those rocks now. Those are broken off pieces of the beach belt series. Oh, but we're going into the archives. And there's the general store. It still pretty much looks like this. Look at the size of these cars, by the way, in 1983, and the huge Coke machine. So I'd be walking back and forth. When a car would pull up to the pump, I'd walk out and pump their gas and then go back and sell rubber tomahawks and all sorts of stuff. And this is the morning of that hike that I was telling you about, the very morning of our group of 4 heading up to Mount Gould. Craig was the leader. Craig was the guy telling me about the beach up on top. And after our beach conversation, I took the photo here because I had a frown on my face probably. I still didn't understand why there was a beach in the mountains. But you can see how high we were. And can you imagine the effect of a summer like this from a kid from the farm in Wisconsin? Had never experienced anything like it. I still have the book that I read the rest of the summer that we sold. I never bought it, I just kind of borrowed it. And I would read and reread that Geology of the Going to the Sun Highway out in front. So when I took a break from working in the store, I'd come out here and sit in front and I'd reread that one little geology book. I've got it right up here on the stage. And one of my jobs with a coworker was to bring this statue out every morning and then bring them back in so nobody would rip it off. And I hope that guy's still there with his cigar. He was the last time I visited in 2010. So this book, written in 1983, just a few months before I worked there, was the reason that I got into geology. There were other things to learn that summer. We don't need to go into that. Kids from all over the country, and many of us working in Glacier Park had music backgrounds. And so for somehow I got to be the little master of ceremonies, like serenading the lodge people. So every Wednesday night we'd have this little group sing along with the guitars and everything. Okay, back to the geology. So look carefully at this map. We've got Idaho and Montana, but we got the old coastline that the belt is telling us about, that the belt rocks are telling us about. And here is a more specific map showing the exact locations of where we can find belt rocks. Notice we are getting into northeastern Washington. Spokane is about here, right? So we've got the corner of our state and all the way down even into the Lemhi Mountains of central Idaho have many of these grains that have been studied very carefully by Paul Link and others. I went on a field trip a couple summers ago just along Interstate 90 near Coeur d'Alene, and Andy Buddington here is in the blue shirt. And many of these photos are from Andy Buddington, who teaches geology at Spokane Community College. Andy was a great help in putting this lecture together. He has studied the belt academically. He worked in the silver mines right out of school as a geologist, and so he knows the Wallace area quite well. And so there's a tie with ore as well and the belt. But anyway, this is just the frontage road. This is the old road right next to I-90, basically, by the best steaks in the world at Wolf Creek Inn or something like that. Amazing place. Here's Eric Cheney from the University of Washington leading us on a small geology group. And they kept talking about Rodinia, and I didn't know what they were talking about 2 years ago, and the breakup of Rodinia. Now we know how Rodinia and supercontinent Columbia fit into this story. So these, if you're a geologist in the room, these are all familiar looking photos. You go out, you stop, you put up a map on the side of the van, and you talk, and then you go point at some more rocks. These are all the belt rocks that we were featuring tonight. So it's the same rocks that we saw in Glacier Park, but right along the freeway. Right there available, easy to stop and look at if you're very interested. More photos from Andy. Now we're into northeast Washington and northern Idaho. We see more of the ripples. We see more of the petrified ripples. Look at how fresh they look, even though they're so old. Mud cracks have different looks. Some of them are truly cracks. Some of the cracks have been filled with replacement minerals. And the stromatolites are found in other places in the belt besides Glacier Park. You've got the point now. We're finding these features. We're finding this consistent beach story for a long time. Even Steptoe Butte, which many of us know as a landmark south of Spokane and north of Pullman, is made out of quartzite. It's part of the belt. It's an island of belt surrounding by the more famous geology of the Palouse. So our eyes are drawn to the Ice Age Palouse and the flood basalts that are beneath the rolling hills. But the island itself, the mountain itself, is from the beach time, from Precambrian days. So not to talk too much about myself tonight, but when I finally went back to Wisconsin and took Geology 101 after that summer in Glacier, I then got a geology degree, and it was time to go to grad school, and I said, well, I'm going to go back out there. I'm going to go study, and I haven't really left the Northwest since then. A photo from leaving, the tearful goodbye with mom and dad and my brand new car for the first time. A Toyota Tercel with no air and no radio and no floor mats and all of my belongings hitting the road and getting out to Teton Park and eventually into the Snake River Plain of Idaho. I went to Idaho State University in Pocatello. It was a great place for me, learned an amazing amount and started teaching there as well. Great. If I had gone to graduate school 200 million years ago, however, there was no reason for me to leave Wisconsin and go to Idaho. There were no mountains at that time. The mountains were in South Carolina because there was no Atlantic Ocean and Pangea was in place. That was the dominant Himalayan-like mountain range at the time. And when we break up Pangea, we take that mountain range, which used to be connected to Africa and northern Europe, and we split it in half. And the Appalachians have been slowly withering away in the last 200 million years. So this familiar world map has half the mountain range from Pangea Assembly here, and the other half of the mountain range from Pangea Assembly there. 300 million year old mountain range, an ocean developing in the last 200 million years. So here's the first of our mind-blowing maps if you haven't seen these before. This is the supercontinent of Pangea. Notice Spokane on the coast. You're like, where's Australia? I thought that was the big mention tonight. It's not going to be on this one, is it? We need a much older supercontinent to talk about the Australia story. I love this, taking today's countries and placing them on Pangea. Let's zoom in on that. So you could go from New York to Morocco. You could go from Charleston, South Carolina to Mauritania. You could go from the coast of Florida to Senegal. Amazing. Pangea, our most recent supercontinent. Now I'm going to drive here. Here's North America, 200 million years ago. I'm getting us to, that's what's familiar. Now let's go back. Let's close the Atlantic Ocean. Oh, you like this. There's murmuring. Okay, this is from Christopher Scotese. There's many of these on YouTube if you look up Christopher Scotese YouTube channel. We're going to do more of that in a bit. Now, this is a more cartoonish version of the same thing I just showed you, and I don't have to control this one. It goes pretty quickly. It's the same idea. We're breaking up our most recent supercontinent, and there's all sorts of things we could talk about, but we don't have time. Now, it's important to notice that when we take two continents and start inching them closer and closer together, we've got to get rid of the ocean crust that's between them. We need to subduct or destroy the ocean crust. So when people talk about quote-unquote continental drift, they fail to factor in the fact that the ocean crust is moving along with the continents. It's something we call tectonic plates. So here's India approaching Asia and not stopping once it kisses Asia and eventually forms the Himalayas that we know and love. So we need to realize that ocean basins need to be destroyed as we do that. So here, between U.S. and Africa, is this wonderful mountain range, the biggest mountain range on the planet, called the Mid-Atlantic Ridge, made out of basalt, that has formed somehow in the last 200 million years. Mid-Atlantic Ridge. It has a beautiful pattern, just like the coastlines of the Americas and Europe and Africa. We didn't know about the Mid-Atlantic Ridge until after World War II. But we now know that that is the reason that let me say it differently. We now have good evidence on the ocean floors that this seafloor spreading and seafloor creation is a real thing. Have you seen this map before? These colors are the ages of the ocean floor. Red is real young. And as we get to oranges and greens and blues, we go back 200 million years. So this was a huge surprise. Why do you have these age patterns that are perfect mirror images of each other in both the Atlantic and the Pacific? That led to this model, which we now fully accept today. In the middle of the oceans, we create crust. And we make a new batch of crust, crack it in half, send half with North America and half with the African plate, and continue. And the continents are drifting away from each other as we create all of this crust in between. It's an amazing collection of data from the oceans that tie with the continents. So the East Pacific Rise, a seafloor spreading in the Pacific, is actually spreading faster than the Mid-Atlantic Ridge. But both are active, and both are part of the drifting continent story. Plate tectonics fully embraced by science, continental drift partially embraced, because during Alfred Wegener's time, he was trying to convince people that continents were somehow moving through old, dead ocean crust, and we now know better. The map that we know well. But now let's go to a map we don't know well. This is outside the copy maker in our building. I look at this every day when I come out of the Xerox room. And I'm like, I got to do a lecture on that. That's such a great display that Walter Zaliga created for us in our new building a couple years ago. What does it show? It shows the old coastline. Do you remember? Here's Montana, Idaho, Washington. There's John Stockton's house in Spokane. There's the old coastline where Australia broke away. at the end of supercontinent Rodinia. There's that coastline today. Now, we're only going to look at a few of these because they are mind blowers. But I'm going to slow down and try to give you a chance to focus on this. This is the best arrangement that we currently have for the old geography of Rodinia. Not Pangea, the supercontinent before. Where are we? There's old North America. There's the belt of Montana and northeastern Washington, and here's the belt continuing on Africa. And remember, we said 750 million years ago is when we started getting Australia to rift away from us. So I presented it in a nice east-west sense, right? But we've got to throw in some other factors here. So you'll see slightly different versions of this map for Rodinia, but this is a fair assessment. This is supercontinent Columbia, the one older yet, the one at the bottom of the chalkboard. And you're like, oh God, what are we looking at? Well, we're looking at a supercontinent, fine. Again, Laurentia is the name we have for old North America. Can I help you? That dot is the belt, and you're like, wait a minute, that dot's the belt? North America is standing on its head. Mexico is up here, Canada's down here. And this reconstruction of supercontinent Columbia has South China as opposed to Australia. I knew this would happen. The energy has changed. The hands are like, I give up. I lost it. I knew that was going to happen, so we're not going to dwell on it. But this is easier to picture. I'm not underselling you now. It's just too much. It's too much. But this is a good representation of 750 million years ago when Australia drifts away from Montana, Idaho, etc. We're going to try this again. Now this guy Scotiste, Christopher Scotiste, is world famous in geology circles. He's even got an animation going back. Look, we're back to earlier supercontinent days. And there's lots of error here, but there's enough to think that we can do something with it. I'm going to try. This, I think I only want you to notice one thing. Here is North America, Canada, U.S., Mexico, and here's our rift. Here's when Australia is going to rift away at 750 million years ago. You ready? And, okay? Now, if you're a great map reader, Scotiste has Antarctica instead of Australia next to us. This is Australia. That's Antarctica. This is Montana. That's Canada. So you can see there's variations just from animation to animation. He's got another one. Is it worth it? I don't know. Enough to just blow us over. Okay, great. So I don't want to show many more of these, but our assumption that North America always is nice and tidy and Canada's up north and Mexico's down, even that is a spinning orb. And the evidence exists for all of that as well, which I don't understand very well. That's enough of these. Oh, this guy, Hoffman, this gives you an idea of how you can try to make a case for a certain continent. Hoffman's an Australia guy. And he says, here's the belt in yellow. There's a belt-like basin in central Australia, another belt in central Australia. Here's Antarctica down here. He's even taking some of another part of old North America and finding it scraps of Australia. So it's a game of positioning old continents and configuring them just right to match up certain kinds of geology. Here's a more recent Rodinia story. Same idea. Precambrian rocks of the Appalachians, follow them through this portion of Australia. And even a younger thing, during the rifting, here's Australia rifting away from us, as it should, 750 million years ago, and some basalts, some Neoproterozoic basins, I guess they're basins, sorry, but we've got the same idea. So it's not just the shapes of the continents is my point. It's using some Precambrian geology in there as well. Oh my God, we got this one too. You want to really get depressed? This is the last 2 billion years of time. And I'll point out, this is us. That's North America, and presumably that's the Montana coast right there. So I think these will change over the next 20 years as we get more and more data. But I'm going to stick with this until we get something that looks familiar. We're not even to 1 billion years ago yet. There's 1 billion. And you're like, please, something I can recognize. Please. Where do I fit in? Hey, all right. Oh, yeah. Okay, great. All right. Yeah, they did a nice job. Should have ended the lecture right there. Okay, a couple more. So you've got headlines like these, and I never really understood how to make sense of the headlines because I didn't have that timeline that we had on the black chalkboard. I needed that personally to know where to plug some of these headlines in. I now am a little closer to that, and maybe you are too. We've already seen that. So we're going to finish where we started, talking about Pangea, breaking apart Pangea, and making the Rock of Washington, with a couple new ideas before we quit. Here's Spokane. Here's all the crust that has been added to the west coast of Old North America since the breakup of Pangea. Those exotic terrains are completely different kinds of rocks with completely different stories of their own. That's a whole nother lecture that we tried last winter. That was a tough lecture to put together. All these scraps of land, these exotic terrains, have their own story and their own origin. If you remember the lecture from last year, the main message was a bunch of those terrains were actually added in Mexico and then got shifted 2,000 miles to the north between 80 and 50 million years ago. Again, this is all crazy stuff happening after Pangea breaks apart. And yes, we made the point that there's growing evidence that our beloved Mount Stewart north of town was originally in Mexico. Are you deeply offended by this? So looking at this map, this is all a very new part of our continent. The youngest and newest arrival, and the last arrival, is the Olympic Peninsula. Before the rock of the Olympic Peninsula was added, the west coast was at I-5. So that's another way to look at this. We tonight have been looking at all the evidence for the coast of North America over here at Spokane, right? That was most of tonight. But the coast starts jumping west as we keep adding crust to the western edge of North America. All of this basalt that runs from the northern edge of the Olympic Peninsula, makes up the Hurricane Ridge above Port Angeles, swings through here by Hood Canal, the Willapa Hills down by Olympia. That's all 55 million year old basalt that originated offshore. A couple years ago we talked about Silesia, a huge chocolate gumdrop out in the ocean. And that's the last of the exotic terrains to add to the west coast here at our latitude. Today we have the Juan de Fuca plate subducting, which is a remnant of the Farallon. But the point is, the age of a huge ocean plate coming at us is about done. And our west coast is going through major changes right now in the last 20 million years. We're realizing it now, that much of the geology is changing. I'll give you a couple of examples and then we'll quit. When we did have that big ocean plate coming at us, it subducted and fueled volcanoes. We still have the Cascades, so we still have a little bit of that left. But we better enjoy the Cascades while we've got them, because they're not going to be with us for much longer. And I'm serious. And that's because this ocean crust coming at us is about to quit. And it's about to quit because we're about to cross, as North Americans, over the East Pacific Rise. You can see the East Pacific Rise today off the coast of South America, but we have crossed a majority of the East Pacific Rise already, and only one little piece of the East Pacific Rise is still off the coast of the Pacific Northwest. When we finish the job of crossing this little spreading center, like California has crossed the spreading center, our volcanoes will stop. The volcanoes will stop, and the volcanoes will not only stop like they did in Eastern California, they're going to physically go away. And the underground magma chamber rock is now up in the mountains. I'm talking about the Sierra Nevada mountains of California today. There used to be Mount Rainier volcanoes in Eastern California, but they have gone through this crazy transformation. And all this magma chamber rock, this granite-like stuff, is now along the John Muir Trail and in Yosemite National Park. I'm saying this is the future of our Cascades. Better or worse? I don't know. Safer? Probably. No big, huge volcanic eruptions. 10 million years from now, this is the scene that will begin, because we will have completed the job of crossing the last little piece of the spreading center known as the East Pacific Rise. But that's not the main thrust of tonight. The main thrust of tonight is this beautiful national park with these spectacular looking rocks, and the rocks with enough details to tell us stories about supercontinents from long ago, including our friend, the most recent supercontinent, Pangea. Thanks for coming tonight, everybody. Sure do appreciate it. Thank you much. Thank you. We'll see you next week.